afternoon, everyone. Let's start the Brain X Lab Day talk concert. We have already have the conference at Pyeongchang for 3 nights and 4 days. So if that is too long, but we have a lot of the idea exchanges and have the connections each others. So I think that that was a good time to share the ideas, to have connections and the friendship. It is my great pleasure to welcome you all to the BrainLink X Lab Day talk concert. I am honored to be here with you. This talk concert is provide opportunity to share knowledge and insight on advanced air mobility. In this the talk concert, we will have the brief presentations about the presentation at the Pyeongchang the conference. So we have 6 the presentation by the co-organized Professor Inman, Professor Atkins, Professor Jurodos, Dr. Brisno, Dr. Choi, Dr. Lee. So I'd like to take the opportunity to thank the Korea Federation of Science, Technology, and Society, Hwachong, and its staff, and co-organizer Professor Inman to prepare this conference and this talk, and provide us with the platform to share our ideas, introduce our works, anything. So I hope that you will have the good opportunity to have new ideas from each other. So now before start the presentation, we will see the movie to explain BrainLink X Lab Day conference and this event. Please turn on the video.
Amidst the world's rapidly accelerating changes and competition, what kind of future are you preparing for? We are chartering a path to the future through science and technology exchanges, bolstered by international cooperation. In this era, where scientific and technological competitiveness is directly linked to a nation's diplomacy and security, the power to overcome such challenges lies in international cooperation that fosters synergy through collective efforts, and from talents who will shape the forthcoming era. The scholars of the world are gathering in Korea. A platform that facilitates exchanges between Korean and international scholars, as well as between seasoned and emerging researchers, is taking shape. BrainLink X Lab Day, organized by the Korean Federation of Science and Technology Societies, aims to be a global hub of talent. By consistently enhancing and expanding the global talent network, we're laying the groundwork for a brighter future. By inviting global scholars, X Lab Day provides an opportunity for young Korean researchers to glean insights from the vast knowledge and experience of both Korean and international scholars, as well as to engage in collaborative research. In 2022, the inaugural X Lab Day saw a total of 14 meetings across various technical fields. Altogether, 449 individuals participated, comprising 70 from overseas and 379 from Korea, all aiming to build a stronger network in Korea and abroad. This year, for our 2023 X Lab Day, we have the honor of having Shing-Tung Yao, professor at Tsinghua University, and a Fields Medal winner. Philip Kim, a globally renowned professor at Harvard University, known for his research in graphene. Yoon Sung Hwang, professor at Stanford University and Hoam Award winner. And Humboldt Research Award winner, Zhigang Suo, professor at Harvard University, leading discourses of their respected fields. This year, the discussions will span 12 national strategic technology fields pivotal to Korea's advancement, including quantum mechanics, nuclear technology, and AI. The event will see the participation of 30 Korean and international scientists and engineers. With 2 organizers leading each technical segment, the gathering will foster in-depth academic exchanges, encompassing the sharing of recent trends and information in core technology fields, in-depth discussions on research findings, and the sharing of ideas. The focus of XLab Day is connectivity and sustainability. Following the event, communities and clubs will be established based on each XLab Day session to ensure ongoing dialogue among attendees and promote collaborative research. To ensure that today's dialogue becomes the seed for tomorrow's magnificent achievements in scientific and technological development, COAST supports the reinforcement and expansion of the networks established through XLab Day. COAST, the organizer of XLab Day, stands as a beacon for Korea's science and technology society. Established in 1966, its mission has been to safeguard and amplify the rights and interests of scientists and engineers. Our endeavors extend to enhancing the public's grasp of science and technology and furthering its development through comprehensive policy research, planning, surveys, and consultations. As Korea's largest science and technology network, with over 600 affiliated organizations, we are committed to promoting domestic and international cooperation and exchange. In the transformative era of the Fourth Industrial Revolution, where science and technology spearhead groundbreaking challenges, COAST remains dedicated to its role as a facilitator of scientific and technological innovations. In this era of technological dominance, we will navigate through the fierce competition by fostering global cooperation in the fields of science and technology. BrainLink XLab Day aims to broaden both domestic and international talent networks and become a global hub of talent. By making XLab Day into an event that scientists and engineers worldwide eagerly join, we intend to elevate Korea's global standing and bolster national competitiveness. Global Talent Hub, BrainLink XLab Day.
Yeah, I would like to introduce the speakers. We have 6 speakers. The first one is the co-organized Professor Inman from University of Michigan at Ann Arbor. The second speaker is Ella Atkins, Professor Ella Atkins from Virginia Tech. Third speaker is Antonios Chourodos, Professor Antonios Chourodos from Cranfield University. Fourth speaker is Dr. Simon Brisno from Joint Air Mobility. Right. Fifth speaker is Dr. Youngjun Choi from UPS AI Laboratory. The last speaker is Professor Ju Young Lee from Utah State University. Now we have the presentation. The first presentation, Professor Inman. Yeah, please introduce yourself briefly before the presentation.
Hi, I'm Dan Inman from the University of Michigan Aerospace Department. I work in smart materials, morphing aircraft, vibration and structural dynamics, that sort of thing. I'm going to talk just a little bit about my, sorry. Yeah, no, it's short, right? Talk a little bit about my concepts of morphing and whether it has any place to play in the space of air mobility or not. Where can morphing improve? Well, it could enhance the endurance and stability and agility and maneuverability of a winged aircraft. There's some concept of controlling over inertia, which is a new idea. And also we embrace autonomy for sensing and control and for noise suppression. Endurance, the main weakness of multi-rotor designs is endurance, essentially. And wing aircraft, of course, have better endurance, and multi-rotor designs have been spiking interest in tilt-rotor craft. You'll see some of that today. And we'll go back in time for the Osprey and Harrier, which were for early examples of that sort of being V-stall behavior and at the same time being able to have winged performance. I've been greatly motivated in the last 10 years by looking at avian, or birds essentially, because of their capacity to change geometry, shape, aerodynamics, and inertia. For a long time, it was felt that their unusual shapes were due to aerodynamics, but it turns out what they're really doing is moving their inertia around so they can change between being very efficient or being very maneuverable. You can't have both. So, and we can see this in design of commercial aircraft versus fighter aircraft. So looking at that, we discovered that really what they were doing is shifting their inertia around, and that allowed them to change their static margins and have variable agility and variable stability. That in turn requires a complex flight controller, which drove us to looking at machine learning techniques to understand how to build complex controllers. Controlling inertia actually should not be a surprise. We all watch the Olympics, and gymnasts, it's exactly what they do to have super agile or hyper agile behavior, is move their inertia around. And you can even do this, an old high school physics teacher, which is how I started out. You'd sat in a chair and move your arms back and forth and create interesting motions. So how to measure inertia is an issue. Are there actuators fast enough to take advantage of that? Does energy, endurance, and weight balance in favor such a system? So there's lots of issues there. These are, as I said earlier, these are TRL-0 concepts, not things that have to do. One place where it might be an immediate advantage is a typical winged V-stall has a pretty short wingspan, because one of the things that it has to do is land in a very small area. And so having wing extension, which actually Professor Bay and I looked at in 2004, and these are plots from that. The red curve shows where the increased in range occurs because of wing extension. Advantages of autonomy: reduce routine task and operate fatigue and quick response issues, such as gust alleviation. Reinforcement learning needs to be balanced against safety and validation, and potential to solve gust issues, endurance issues, and stability issues. So the other thing that happened is there's been quite an advancement in embedded computing chips and learning algorithms and autonomy, starting out with microcontrollers and ending up now with memristors and other things. They're very small, they're very fast, they don't use a lot of heat or energy, they don't use a lot of energy or generate a lot of heat. So that means that's all good news for V-stall and eVTOL characteristics. Just an example, a memristor state inference for gust measurement, which we've successfully done, at least in the wind tunnel. And then a summary for morphing. Given multiple constraints, a vehicle designed for AA must satisfy radical shape changing, or morphing may provide viable solutions to move forward. So long endurance, high agility, help to satisfy weight and volume restrictions, and expand the use space. And for that, I'll rest my case. Thank you very much.
Thank you, Professor Inman. Our next speaker is Professor Ella Atkins.
Hi, I'm Ella Atkins. I'm a professor and department head of aerospace and ocean engineering at Virginia Tech. I was a colleague of Dan Inman's at Michigan for many years before that. My area is in both computer science and aerospace, which means in putting them together, you focus on autonomy. So the title here has two things in it. One, contingency management. What happens with the autonomy when things go wrong? How do you prevent crashing? And the other is airspace management. And there, we have a lot of work ahead of us to make sure that these new aircraft can share the airspace with existing aircraft. And all the new aircraft come in many sizes and shapes. This first slide really shows where we are now and pathways to get to where we might go in the future. The top line, if I can get the laser pointer, maybe, yep. I don't know how to do the laser pointer so well, so I'll just ignore it. But anyway, the top line starts at the left with any sort of aircraft that exists today. You have one or more crew members on board that are flying the aircraft, increasingly with fly-by-wire avionics. But the people are responsible for looking out the window, monitoring all of the instruments, and making decisions. To go from here to autonomous or advanced air mobility, for me, autonomous goes along with it because of the scalability problem of having enough pilots to fly these vehicles. We end up first going to simplified vehicle operations, or SVO, which means we have low-level automation to help the pilot, the single pilot, more than is done today. Next, we go to moving the safety pilot to the ground. This takes that extra weight and volume off the aircraft to maximize the number of passengers that can actually be there. And then finally, we get to an increasingly autonomous, if not fully autonomous, flight. Well, the reason I have this thing on the bottom is because when we talk about uncrewed aircraft systems, or UAS, the pathway looks a lot different. We start out never having a person on board, which means that we need a data link immediately. And then we go to having trials of larger vehicles, different airframe concepts, new instruments, better maps, and we go through a pathway to where eventually we need to certify those vehicles and their operational profiles and get them all to share the same airspace. I have a moment of quiet there just because sharing the same airspace means that the small handheld quad rotor and the passenger carrying advanced air mobility vehicle ultimately may pass each other, safely separated but still in the same volume of airspace. So contingency management. One of the reasons that I've focused long-term on contingency management is because the human traditionally has needed to make a lot of difficult, intense decisions when things go wrong. If you're in a commercial aircraft, if something is beginning to go wrong, your goal is to land. If you've learned to fly, the column on the left talks about what you do. First of all, you aviate. That means that you maintain stability of your aircraft and you keep flying it. You don't get distracted and end up in trouble because you're not flying your aircraft. Next, you navigate. You have to know where you are, where you're going, and make decisions about safety and landing. Finally, communicating. You have to tell everyone else in the airspace what you're doing to make sure that they are aware and can stay out of your way. If we go to the right-hand side, this shows how those simple rules that a pilot is told to follow every time they have an emergency or urgent situation to what autonomy would do. Well, first of all, you want to control the aircraft. You want to adapt as needed if there's problems with the control surfaces, with the motors, with the structure, and make sure that you remain within the envelope, the safe flight envelope of the aircraft. Estimate where you can go, project the range that you can get to, choose a landing site, build a flight plan that works, given potentially reduced performance, to reach that site, and then execute it to actually get there and safely land. This is pretty old work. The strange yellow diagram on the left is basically a restatement in a very simple form appropriate for fixed-wing aircraft landing on a runway. That diagram I made in about 2002, and it applied really nicely to this accident case of U.S. Airways 1549, where they ended up in the Hudson River. Everyone lived, but the aircraft obviously was not salvageable. So the first thing that you do is this footprint generation, which is finding the range, finding the landing sites. In this case, it's a list of runways because a large commercial aircraft doesn't land well in a small field or even in water. And then make sure they're long enough, wide enough, the winds are suitable, choose the best one, build a plan, and then go there. So the data on the right really accentuates that we're not doing any simple or anything complicated with machine learning or AI. It's just geometry and ranking landing sites. And simple is good when you have safety critical automation in aviation because you can certify it. We have the process today to do that. So with this type of tool, you can end up helping a flight crew if you're not autonomous. So if the pilot Sully had this information, he would have been confident that he could have gotten back to LaGuardia instead of landing in the river. The story would have been quite different. We probably wouldn't even have heard about it in the news, right? And also this accentuates the importance of having a data link for the aircraft to communicate with all of the other aircraft and air traffic control, because in this case, the health management system, the sensors and the engines knew there was a problem, could communicate that. With this flight plan, everyone else could have been immediately told to get out of the way. That didn't happen. No one did anything wrong, but voice is slow. So if we are looking at large aircraft, we have to look at runways mostly if we want to land safely. But the other end of the spectrum is the small uncrewed aircraft system, or UAS. For that, we can land in a lot of different places. They're not heavy, they're not going to break through the rooftops of buildings or anything like that, but we really don't want them to land in populated areas because they can pose risk to the people that are outside in those areas. So a lot of the work that we did in this focus on identifying and mapping landing sites for small UAS focused on taking data sets like LiDAR, satellite, and then some kind of database, in this case OpenStreetMaps, which is free to everyone, processing it in a way that allows us to find landing sites even in very densely populated urban areas, and then ultimately building flight plans as needed for a safe landing. We have two risk metrics here. One is the landing site risk. We're not landing in a prepared area. We're landing somewhere that there might be things or people, and so there's risk. We also want a big sized area as opposed to a small area. There's some kind of metric or score for that. We also care about path risk. What are we flying over to get there? We know where we start, we know where we end. There's both of those metrics. Well, all of that data has to be processed somehow. So one of my students, citation at the bottom, looked at this algorithm called PolyLiDAR 3D that finds dominant planes from LiDAR point clouds. To do that, this is 10 minutes, so I can't explain the details, but basically what happens is whatever data you're collecting from an airborne source, LiDAR data, vision data, both you can put together, you want to find and inscribe circular flat landing sites wherever it is. So we focused on rooftops because that is really an area that is underutilized today in terms of being able to put something down in an emergency so that you don't end up impacting something on the ground where the population is. So in this case, you can see we take a flat roof that has infrastructure on it, find the outline of the building edge and obstacles within the roof, and then we inscribe circular landing sites in that area to find them. What you see on the bottom right is a Pareto front map that shows of all the landing sites that in this particular case a UAS could reach. We're really looking at two different metrics, the landing site risk and the path risk, and we of course want to get that bottom left corner solution that minimizes both. So the second thing that I want to at least highlight very briefly is a potential airspace solution for very low altitude. This is not replacing what commercial aircraft use today to go into major airports. This is looking at the huge variety of missions that small UAS will actually have. Many of them are over a particular area. Let's say you're doing a wind turbine inspection or a bridge inspection or something like that, looking at a crop in a field. Well, when that mission is happening, you want to put some kind of box around it, an airspace geofence, and say, hey, nobody else should fly there while that mission is happening. And as long as you avoid that box, it really doesn't matter what's inside that box. So you're effectively abstracting away the detail of what that UAS is doing, but it's safe because that airspace is temporarily reserved. There would be static geofences that would be permanent around buildings, power lines, cell towers, other obstacles that are potentially sensitive areas where you never want anything to fly. So this little animation on the right is showing how if you have a vehicle that is traveling, this little cylinder is surrounding it, it can navigate through the static geofence, which is blue and there all the time, and the durational geofence, which is green, and only there when you have a UAS operating in that area to coordinate those missions. So this is an example where I think the right-hand animation, actually they're both going at the same time, that's good. So what happens here is we have two durational geofences. The blue one shows up early on, and we have a vehicle shown by the little dot going from right to left on the right-hand diagram that represents the UAS trajectory going through the yellow tube, which is the trajectory of that vehicle. They all have to be deconflicted, and so what's happening here is that vehicle speeds through the first part of its path before the green geofence becomes active that represents another mission, and then it slows down because it knows, based on what the air traffic or UTM system has, that the blue geofence is going to end. So this way it's able to fly the entire mission without coming to a stop anywhere and avoiding two separate other flights that occupy the airspace. So one of the things that's kind of cool about this is that by using polygons with fixed ceiling and floor, you end up with a very computationally efficient representation where you can use set operations with these polygons to deconflict an arbitrarily complex in number and in shape set of geofences. With these geofences, obviously you have to worry about keeping the vehicle in them. So you have layers. What you see on the top is two different geofences. You must not go outside the outer boundary. But the green on the inside is a warning layer where to the pilot or the automation you're going to say, hey, you're getting close to the edge. The blue is an override layer where the automation would turn the aircraft back before it got to the edge. And what you can adjust these for steady wind and so on. When you put them all together, you end up with a solution that to the vehicle looks like a pipe that it should stay in at all times, or a polygon. To UTM, or the air traffic control system, it looks like airspace volumes that can have any shape or size. They can have a time duration, and they can follow the vehicle through the paths that it needs to go in. Why is this a good solution? Well, the reason this is a good solution is because if we were to make corridors that were fixed and stay there all the time, we are going to have a much harder problem to get a lot of vehicles to do the missions that they want to do. Whereas this is going to be able to use all of the airspace. So as we look at the geofences and the small UAS flying, whether they're having any sort of emergency or not, this is not something that my group does a lot of, but we have to model the wind, because if we're in an urban canyon flying low, the wind has a huge impact. This is one example, and this example just illustrates how much you can see with the different shadings on kind of the diagram on the right. The wind, even a steady predominant wind, can vary as you go around buildings. That has an impact on the geofences as well as the flight plans. So the buildings here you see in green have the geofences around them. They're keep out, meaning you can't go in and hit them. The flight trajectory, the flight plan that we ultimately calculate in this case is taking into account where the vehicle is expected to blow in terms of wind and the error that it might see because of that wind and the changes in it as it goes around buildings. And then also that airspace around the vehicle is surrounded by a polygon with fixed ceiling and floor to make sure that that aircraft remains safely separated from the buildings and then any other aircraft in the vicinity. All right, thank you.
Thank you. Next speaker is Professor Antonios Troodos.
Hi, I'm Antonio Troodos. I'm from Calvi University, where I'm leading the autonomy research area for the university. And as you can see, that the university is in UK and it is built around an airport. So it is the airport with a university, as the airport said, or a university with an airport, as our VC says. We have developed the ecosystem. It is the main concept of the Digital Aviation Research Technology Center we have at Cranfield. And that is looking at different parts of the ecosystems. The conscious aircraft, which is, how can be self-aware, the platforms that goes there, so to be able to say what is the state of that one, if it has a problem or not, so to be able to know how we distributed the airports around and the vertiports and the airspace management around them. How do we put in unmanned traffic management in this airspace? How we can connect the various players in the airspace, and of course it is how we can look in the journey of the passengers and make that as comfortable and seamless as it is. And we look in the different parts of that ones in the center. Now we are lucky that the airport it is one of the test beds for the UKRI Future Flight Challenge, and the airport has work with the Civil Aerospace Authority in UK and has created a temporary reserved area that enables us to connect the airport with the neighbored city and will be able to operate manned and unmanned aircrafts in unsegregated airspace. And we try to see all the technologies that will enable that to happen safely. So within that program, we start looking in order to achieve that once. We had a program with skyports and drone clouds and frequencies and skyports to start looking how we can integrate a UTM system with the ATM system of the airport, and how can they work in them together, even if they are not co-located. It can be one in the city, one in the airport, but they have to working seamlessly one from with the other. And we tested that around, along with the communications that they need going from one system to another. Then we start looking about the connectivity. When we start going the platforms through the very different network systems and providers, how can we maintain the chain of trust of them? So how we can make sure that we don't open vulnerabilities of that ones, and we can identify and authenticate each one of them. Then we start looking slightly larger. We start looking about in an airport environment, what kind of changes in technology we have in order for the unmanned systems to communicate with the ATC controller, and what kind of changes have to become to the airport to enable to having the unmanned systems and manned working together. We start looking about what kind of communications that we have to having an information exchange in order to enable to increasing the density and capacity of the space around the airports. And we start looking what is the blockchain technology can bring inside that ones in order to enable the information's data exchange and improving the capacity and density of the airports. Then we start looking slightly larger. projects, and we start looking if we're having many different airports. Here it's the London City, the Bristol, the Heathrow Airport, and we start putting advanced mobility platforms and vertiports. Where do we locate? How we can link the platforms with the vertiports? How can we link the vertiports with the airports? What kind of changes we have to do both on the design of the vertiports, on the platforms, and on the airspace? We're looking about if we're looking more on more busy airports, what kind of other technologies is needed? The country UAS that can be there in order to make sure that we're having only legitimate movement and not unlegitimate. How can we identify how the country UAS systems with the UTM service providers and the ATC can work together, and what kind of information we want to have? We're looking also how we can putting that into the logistics, and that's what we're looking with the blueprint. How we can having smaller providers in more sub-regional areas, suburbs, and satellite cities, and what kind of technologies we have to have there, what kind of changes we need to do there. And then we start looking about the wind. If we're putting vertiports into the airports, do we understand, or in the middle of the city, how can we having the wind analysis of the areas in order to make sure that not only we located in the right place, but also we having the flight clearances from these places to be linked with the capabilities of the platforms. And then we start looking, if we're putting too many systems together, we need to start seeing how do we synchronize them, how we can having information that can be trusted, that they are time-stamped in the right way. The frequencies and times between the different providers are in synchrony, and we don't creating potential fatal errors down the line. And we can see how can we have the resilience of that ones. That means can we rely not only in one system like the GNSS timing synchronization, but also on ground-based systems, and how can we go from one to another and complement in order to increase the resilience. Then we start looking at other enabling technologies. When we moving and flying the platforms, they're going from urban to non-urban areas. They're going from different networks that it is provided in connectivity in the urban areas to more satellite-based connectivity in the non-urban areas. How can we going from one to another and having a very seamless handover from one system to another, from one connectivity network to another, without losing the quality of services, but not also open vulnerabilities to the systems. Then we start looking about the navigation systems. I mean, we need if we can know the quality of services of the position navigations on the area we are moving, then we can know where it is a different risks, where we're having areas that they are not very well served by the GNSS, and then we can start to seeing what kind of alternative solutions we can have to put in place in order to having the resilience and assurance that we need on the navigation and positioning of the platforms going around. And then we start looking how can we put them together. If we having that ones in the mission planning, in not having routing and traffic management that it have only the fastest, most more efficient in the distance-wise or fuel-wise paths, but also the ones that give us the assurance of the safety of the platforms. That means they can give us the quality of service and connectivity and the positioning and navigation and synchronizations. And we're putting them together and we design paths that they say, this is the ones that we're giving the better mission success rate on the routings. And putting them all together, then we start looking how can we having the locations of the different vertiports and how can we increasing the capacity of the airspace, taking into account the quality of services on the PNT and on the communications on the areas, while we're increasing the volume of movements. And we take into account the existing capacity of the airspace, what is the different movements during the day, and then we're putting on top of that the vertiports in the different locations and say how we can also operate them, and take into account that these areas we need to take in the safety based on the increased quality of services on navigation and communications. And then we can start seeing how we can making the deconflictions and while we're increasing the capacity. And we do see here, and that you can see on the graphs, the more we're having a trust on the positioning and the communications, that means we can reducing the uncertainty around the movements, the more the deconflictions are disappearing. The more we start losing that trust, we means we're increasing the uncertainty around the positioning and the communications, the more deconflictions we have to do, and that has an impact both also on how many platforms we can put on that around, but also how much rerouting and ground delay and however we need to do in order to deconflict them. So that comes all of them together. And I will finish here with, now we start working with the city next to us and the regulator, which is the CAA here, to start looking how we can create the environment in the city. So we start looking there, how can we improving the quality of services on the positioning, on the navigations, what kind of sensor we can put in there, where are we putting the different drone ports around in order for them later to become vertiports, and in order to be able to having multiple UTM service providers and different operators working in the city for both logistics and other services that it is going around the environment. So we're creating a live test bed in a city, bringing all of them around. Thank you very much.
Thank you. Next speaker is Dr. Simon Brisno.
Hello, good afternoon, everyone. My name is Simon Briseno. I want to start by thanking Professor Bay and the COAST organization for putting this together. I'm honored to be here. So this is a little bit different in terms of my background. As I have down there, I'm ex-research faculty at Georgia Tech, spent many years in aircraft design, conceptual aircraft design, systems integration, and looking specifically at advanced aircraft concepts, in particular for the electric aviation field. And then I joined Jaunt Air Mobility, and we are a company that is designing, developing, and certifying an eVTOL for the advanced air mobility markets. Hopefully here in this short presentation, I just want to pinpoint some of the key areas that I think are really critical right now in advanced air mobility. But first, let me just start by introducing our aircraft. So we have a very simple aircraft design. We're taking the best attributes of vertical flight and horizontal flight. So if you look at a traditional helicopter, a single main rotor, that's the most efficient way to fly vertically. And if you take a high aspect ratio wing aircraft like a sailplane or a glider, that's the most efficient way to fly horizontally, high L over D ratio. What we did here is combine both, and this concept is referred to as a compound because you're adding both a single main rotor and a fixed wing, compound rotorcraft. So we are a rotorcraft. Some of the key areas, the main rotor is very unique. It actually slows down in cruise flight. And this is really important because we're able to fly faster. Some of the issues that helicopters have, the main issue, is that they can't fly fast because of retreating blade stall. They're limited in terms of that speed. We don't have that problem. Our aircraft takes off by powering the main rotor, and then we transition into forward flight, and we slow down the main rotor, and the weight of the aircraft transitions onto the wings. We have 4 propellers that provide the control authority or the anti-torque to the main rotor. We have a lot of redundancy. We can lose a pair of those propellers and still have full control. This is really important for gust alleviation and low speed, low altitude maneuverability. You can see some of the performance aspects here. So the aircraft is going to be certified for single pilot IFR operations. We're going to be able to carry 4 passengers and the equivalent payload in terms of cargo. We're targeting the air taxi and cargo markets, which I'll talk about here in a minute. And the last thing I'll mention here, it's really important for public acceptance to have a very quiet aircraft. And by being able to slow that main rotor in flight, you really won't hear this aircraft fly overhead. For us, and as for obviously most aircraft design and certification, safety is absolutely number one. It's paramount. We have a very unique ability to auto-rotate. We have enhanced auto-rotation capabilities, unlike a traditional helicopter. We're able to land from any altitude or speed and land vertically with no forward speed, unlike a helicopter that has to flare. And we have that because of what we call a high inertia rotor system. We have weights on the tips of the main rotor, and once we have that rotor spinning fast, it has a stored energy capability. And so in the event of a complete power loss, we have that energy that's stored in the main rotor, and the flight control computers, as a full fly-by-wire aircraft, kicks in, and it controls the ability to use both the fixed wing with the control surfaces and the energy in the main rotor to land virtually anywhere. And this is really critical for urban flight. Just briefly, where we are in terms of our development, we have a jaunt technology demonstrator that has been flying for the last 5 to 10 years, and really we use this vehicle to mature the main rotor design itself. The most difficult and challenging aspect of helicopter or rotorcraft design is the main rotor, and in particular in this case, the ability to slow that in flight. As you can imagine, it creates a lot of stability and mechanics, aeroelastic considerations. So this aircraft has flown, piloted, and has had many flight hours to, again, prove and mature that main rotor design. Switching gears a little bit, just some highlights about our company. We are located, in terms of our design and manufacturing, in Quebec, in Canada. Quebec and Montreal have a rich history of aerospace with a lot of suppliers, Bombardier and others, of course, working there. We are type certifying our aircraft with Transport Canada. Transport Canada has actually certified all of Bell's helicopters since 1982. So they have a lot of experience with rotorcraft. And of course, with the FAA and EASA, there's a bilateral agreement. So you certify with one, you're effectively certifying with all of them. These are just some of our key Tier 1 suppliers. BAE Systems doing our battery management system and flight control computers. This is a key, probably the most critical area for eVTOLs and advanced air mobility is developing the battery system, being able to deal with issues like thermal runaway, cell-to-cell propagation. This is a hot topic in certification as well. I'll talk briefly about CAE here in a minute. Carbon Aerospace is doing our thermoplastics, so we're actually building our entire structure. Fuselage is made out of thermoplastics instead of traditional thermosets or composites, and this is for mass production reasons. We're working with the Canadian government, and of course we have a diverse customer base globally with operators in many different types of use cases. CAE is world-renowned in pilot training, but many people don't know they actually are leading as well in engineering simulators, which are really critical for doing testing and evaluation throughout the design and development and certification process. They're developing our systems integration lab and really helping us accelerate the development time by doing a lot of that testing on the ground. They're using some really cool, innovative technologies with augmented reality capabilities. And again, this is another area of a lot of research, both with academia and industry. Certification, a very hot topic, probably the biggest topic right now with eVTOL manufacturers impacting their program development. And this is a chart that was developed by the FAA, just showing the various types of rules and how they differ in terms of the societal risk. We are developing an aircraft that will be operated commercially, and so in our case, it's really important to meet the transport category requirements. There's a lot of debate right now between EASA and the FAA on what that level of rule set and standards and means of compliance should be for the advanced air mobility space. Just a little bit more detail in terms of the differences between what some other manufacturers are doing and ourselves. We believe in things like bird strike. You're going to see that in low altitude flight. It's really critical to be able to design to those rules and standards, as well as damage tolerance and fatigue tolerance and some of the other critical areas as well. The market opportunity is very large. Many studies have been performed over the last decade showing that there's going to be an increasing demand of aircraft over the next 2-3 decades. A lot of different use cases. Most people know about the air taxi, but there's middle mile freight and cargo that I think is very critical and will most likely be an early adopter of these types of aircraft. This is just an example of in New York City, how this aircraft would fly between Manhattan and JFK Airport, and this chart just shows the depletion of the battery over time and recharging at the destination for just a little bit to be able to extend the time of that battery and that aircraft throughout the day. And finally, I just wanted to show some of the additional critical elements to make these aircraft actually put into commercial service. From an operator standpoint, you have a lot of considerations to have, and their customers as well, how you're able to put all of this together on various platforms, both digital and physical infrastructure that will be needed to make this a reality. So it's not just about the aircraft, it's the whole ecosystem. And so these are some of the areas that we're working on, and a lot of these areas still require a lot of research and collaboration. I have, I think, one last slide just showing some of the future concepts for unmanned, uncrewed air systems that we have as well. Our air technology scales down really nicely to a whole host of other applications when you're uncrewed. And with that, I'll end.
Yeah, next speaker is Dr. Young-jun Choi.
Hello everyone, my name is Young-jun Choi. I'm a Director of Advanced AI and Robotics. This is a very exciting time because if you see the technology evolutions, eVTOLs, generative AI and robotics, right? There are a lot of things happening right now. Today I'm going to talk about the title from reactive to proactive, because if you see like current our logistic operations, it is a little bit reactive because there are still a lot of manual human-based decision-making process. Here what I want to do is we want to apply the data, digital themes so that we can improve our network. Here my talk is focusing on how we can develop the digital twin network with advanced air mobilities. Okay? So first, before talking about this, I want to ask, how many of you know about the UPS? Great. So UPS is a delivery company. We are delivering 25 million packages daily. We are delivering 220 countries in the world. Right? Also, we are moving 6% GDPs in US and 2% GDP in the world. Okay? So the foundation is smart logistics network. It is a combination of data and emerging technologies, including airlines and ground assets, like package cars and trailers. This network is very resilient and self-healing. It means that if something happens, it can automatically reconfigure the network so that we can continuously provide our best-in-class service to our customers. Let's deep dive about self-healing smart logistics network. Simply, it is elastic, it is self-healing. Okay? It means that there are four main objectives. Our company, customer-first company, it means that when we build our network, first, we are thinking about our customers. Okay? We try to thinking about how we can improve our customer service. That's the first thing. And the second is how we can build an efficient network. And the third is how we can improve our revenue streams. It means that if you see like recent announcement, our UPS, we try to build a logistics as a service. It means that we want to use the data and also new visibilities so that we can provide a new visibility service. Last but not least, sustainability. This is a very hot topic, right? Electrified asset is one of the core technologies we want to apply in our network. Our UPS, we try to build a green network by 2050. Okay. So I'm gonna talk about very detailed about smart logistics network. Before talking about that, I want to highlight the customer satisfaction, right? When we measure the customer satisfaction, we use a net promoter scores. Maybe when you use our package delivery service, they're gonna ask, do you recommend this service to your friends or families? That's the net promoter score. Using this net promoter scores, we are measuring our customer needs. And then from them, we try to build our network. Let's deep dive our network, okay? In terms of transportation side, as you can see there, the top, okay, there, okay. There is smart package, smart facilities, okay? Basically, our UPS, we try to apply the RFID sensors on the individual packages so that we can track the individual package journeys in our network. Because conventionally, we are using the labels, right? So now, we are trying to transform using the RFID sensors. Second, let's look at the delivery fleets. So UPS, we have 100,000 ground assets, including package cars, trailers, shifters, and so forth. Also, UPS, we have 500 aircraft. I look at the Korean Air number of fleets. They have around 150 fleets, okay? And then 23 fleets are for cargo, right? So if you can imagine our scales. Right? Also, UPS, we are very innovative company. We try to adapt to emerging technologies. It means that, as you can see here, drones, eVTOLs, and also we try to adapt autonomous mobile robots in the warehouse environment, right? And then also, as you can see here, there is a transportation management systems. We are thinking about how we can orchestrate all different heterogeneous platforms. And also we have network planning tools. It means that when you move the volumes between the hub to hub, right, we have optimizations. It means that depending on the volume changes, it automatically reconfigures our network so that we can continuously provide our best-in-class service. Let's look at the in-buildings. UPS, we have 1,400 buildings in US. Right? Also, I want to emphasize that UPS is a data-rich company. Every day, we are collecting over 1 billion data set. Using this data, our data science armies, they try to understand the delivery trend, also customer trend, and also we try to understand what is the network efficiencies. And another aspect is that our scientists try to adapt AI and machine learning and computer visions so that we can have better network efficiencies. If you look at the final miles, we try to provide a better service through applying smart access point. Also, we have a well-known tool, Orion, which is a dynamic last mile route optimization tools. It means that using the traffic signals and weather data, also based on the customer demand and time windows, we try to provide the best route so that we can provide on-time delivery service. So this is a kind of big picture of smart logistics network UPS is seeking. Okay. So now I'm gonna talk about digital twins, right? I just talked about smart logistics network. Now UPS, we try to use the data and simulations so that we can improve our network more proactive ways. Let's look at the more details. So let's say we have package data, which is like demand signals. And then we have a network signals, I mean the weather data and traffic data. Using all those data, we have like digital replica of entire network. It means that using the data and simulations, we try to understand what is the upcoming bottlenecks, right? Based on those informations, we have AI and machine learning engines so that we can proactively mitigate those kind of risks. So this is our digital twin team. Our UPS is continuously building now. Okay? And here, we need to think about advance of air mobility roles, because our logistic perspective, we are heading to like digital twins, right? I know here like there are technologies to try to build like eVTOLs, right? But in terms of business perspective, right, this is not enough. This is not enough. We need to minimize the gaps between the UPS digital twin teams and also the technology eVTOL we are building here, right? So here I put like 3 different videos. There are several activities UPS have done. The first one is using the drones. We did medical equipment delivery service, working with the WakeMed, okay, which is the campus delivery. And then second example is UPS try to do very innovative concept. It means that we try to combine it with a package car plus drones. It means that we launch the drones from the package cars so that we can improve last mile efficiency. Last video is we are, as you know, like we are closely working with Beta Technologies, because the Beta technology platform can be a great platform. We can move the volumes between the hubs. So now I'm gonna switch the topic about like eVTOL conceptual design. I just talked about the complexity of the operational concept, and also there is a lot of things we need to consider, like constraints or different eVTOL concept. Here, here I'm gonna talk about one of our research when I was a research faculty at Georgia Tech Aerospace. It's about how we can do better conceptual design in the early design phase. So when we design the eVTOL like drone systems, right, we need to thinking about many different aspects. Vehicle constraints, right, thinking about what is the recharging mechanisms, and also different concept of operations. Also, we need to think about regulations. And in terms of logistic perspective, business is very important, because we need to think about what is the like package demand and what is the time windows, right? Then when you design the like eVTOL and aircraft, right, in the classical way is that typically the mission is given. It means the mission analysis or operator like UPS give here is a mission profiles, and then aircraft designer use the like sizing and synthesis tools, and then optimize the vehicles. Okay, let's look at the fleet size, fleet perspective, right? Operators, typically we have a notional concept of the vehicles, right? And then based on this concept, we have a set of constraints and cost functions, and we try to optimize all those routes, right? This process is decoupled now, right? So here we try to come up with iterative concept so that we can combine all together so that we can have a better optimization result. So as you can see on the right side, this is a concept. Instead of decoupled optimization schemes, we try to combine two optimization structures. So one is optimize the sizing and synthesis, and then the other one is optimizing the fleet route. There are a lot of things going on, so today I just want to highlight like key stuff. Here, basically we're gonna use the airborne LiDAR sensor data, and then FAA regulations, and then with the AI and machine learning algorithms, try to come up with the flyable routes, and then based on the set of constraints, we optimize the fleet route. Okay. So here I want to share like one of the route optimization result. So this is the San Diego areas. So we use the airborne lidar sensor data, and then there is a multi-million point cloud informations. And then as you can see here, there is lines. It's about the delivery routes based on the demand data and also FAA regulation informations. As you can see here, our route optimization framework can provide collision-free delivery routes for the drones. And then, as you can see here, if you see the total in terms of vehicle total weights and cost, total cost, it's better because now we can combine all together and then we can see all those coupled impact. So this is my last slide. UPS, we are a very innovative company. We are seeking the digit twin network. So here, one of the important things is that how we can minimize the gaps between the digit twin network and current advanced air mobility platform we are building here. Right? And then second, I introduced novel MDO framework combined with the sizing and synthesis, plus and also fleet optimized structure. Thank you.
Thank you. The last speaker is Professor Ju-Young Lee.
Thank you for attending my talk. So my name is Ju-Young Lee. I'm an assistant professor in the mechanical and aerospace engineering at the Utah State University. The UAM, urban air mobility, advanced air mobility, is a very new market. That means we need a lot of expert within the many different disciplines. So in contrast to other presenter, my specific research focus is how we can make UAM structure. What's the best solution that minimize the weight but while maintain the good structure performance. So I have a research interest in the high performance, multifunctional composite, and how this structure behave on the extreme environment. So today's talk will be like a novel structure concept using origami and kirigami based sandwich panel. So this is the collection of all the commercially available or the soon to be available the UAM aviation industry. So including from Joby Aviation and Vertical Aerospace, Lilium and Volocopter and the joint aviation stuff. So if you think about the material system and then how the way to make this critical component using all this selected material, we also have to find the best manufacturing process. So for example, if you're looking at the Joby Aviation, and they use a bunch of carbon fiber, epoxy, thermosetting, or prepreg. And also they're using a traditional compression molding process plus automated fiber placement technique to make a lightweight component. So there are some very small sections that they use additive manufacturing, but predominantly they focus on making some metal part using additive manufacturing. And they consider the future, the material will be the thermoplastic material, and also they want to make all the part at auto mold process, and also they want to make all the component with a very short time period. So if you're looking at the other aviation industry, in the same way, they use all the thermoplastics and then AFP, auto mold, autoclave process, additive manufacturing, and etc. So if you think about the domestic kind of aviation, kind of the brand, I included the photos, the Hyundai Motors, the Supernal, and Oboe, and the Hanwha Group. If you think about the primary and the structured aviation application, our main focus is to make something lighter but stronger, because the light, the weight and the performance are always trading off. If you want to make something large, that means you have to reduce the total weight of your vehicle. So when you design the advanced air mobility and then choose the material system, there are many different aspects based on the structure requirement. So this photo shows, depending on your application, there are different functionality as well as mechanical performance. So if you want to design the aviation or the UAM structure component, of course we have to use a certified material. We can't simply use a new material by just simply formulating some internal component. So we have to choose some certified material that are already existing in the database, Also need to think about like damping, sound absorbing, and then like a weldable, because we can make this entire vehicle in a single piece. That means the small, like thousands of the small pieces will be bonded and jointed to make this kind of big picture. So also the energy absorption is one important aspect when you design the structure. And also when you think about the external skin part, maybe increase the mass production, we have to use kind of the various process to make a small one and a larger one. So scalable manufacturing is a key part when you design the panel and the cover and all the communication system. And also when you try to operate this UAM system in the very extreme environment, let's say in the rainy weather and then with the thunderstorm, you have to protect all your kind of system from all the natural icing issues and lightning issues. So galvanic corrosion is one of the big issues, and the lightning protection. So when I summarize all the future selection of the material system that we can use to advance air mobility, the people use a lot of thermosetting material system, and Solvay and Cycom, they use traditional carbon fiber epoxy prepreg. And the second choice, the second recommendation from the manufacturer suppliers and OEM, they mentioned the snap cure resin. The snap cure resin means you can make the part. The thermosetting resin can be cured in the 1 minute. And then obviously we have a very big future when you use a thermoplastic material. The main difference between the thermoset and thermoplastic means you can actually optimize or maximize the production rate. And then in terms of the fabrication process, people use a traditional hand layup and autoclave cure, AFP, and automated tape laying kinds of process. And also the people gradually use additive manufacturing to make the polymer or composite part. And also, whenever I talked with a composite material supplier for the UAM division, they say the common things. They are going to use existing traditional legacy aerospace material system until the UAM market is large enough, because it's a very high risk, and then they don't want to simply change the material system to increase their mass production. So change in the material selection will be made only the market size and the volume will be very, very large enough. So that's a kind of one limitation when you do some composite-related research at the academia. So, but basically, all the aerospace material systems are expensive compared to the automobile sections and the civil infrastructure. So it's very expensive, but high quality, and the manufacturing process are somewhat kind of lengthy and kind of long time. So aerospace materials are also required to meet the safety requirement. So when you make a UAM, a PAV, you need to think about the safety of your passengers. We can't simply use the random material, and then that will cause a lot of legal issues. And also, the aerospace materials are required to be selected from kind of certified database. So we have a restriction. We have to choose this material system from the database that include all the certified material. So if you think about the future, near future application, and using the same or existing material system, how we can optimize or maximize structure performance and increase the payload while still minimizing the weight, cost, and leading time. That was my kind of the motivation of the research. And after a month of thinking, I thought about whether we can use kind of traditional like a folding and cutting technique to make a structural component. So most of you hear the term called the origami and kirigami. So simple definition of origami means you fold thin material, and the kirigami means it's a cutting. So when you actually fold and cut to make some part, that's a hybrid origami and kirigami structure. That's a simple definition. And if you want to make some deformable, that means you have a soft, foldable, some like a deployable space structure, that will be considered as kind of the deformable category. And also if you want to make something fixed and it's very hard, and then that's a kind of rigid core. So depending on our target application, we may use a paper and the metal and the composite. And composite, we have a lot of different choices starting from the polymer and hydrogel and graphene. So if you use the composite material system while reducing the weight of your kind of structure, you can maximize structure performance. So here, these are the collection of some origami and kirigami folded core geometry. If you're looking at the top two images, that's a legacy honeycomb core. So you have a square honeycomb and hexagon honeycomb. It's there. We can simply change the shape or range of this cell. And also, if you're looking at the middle section, we have a origami folded core, starting from the standard, the Miura folding, and the indented core, and other tessellation. But these are historically made using metal or the paper, and you may see some artistics. I mean, they use all kind of paper to make beautiful kind of the structures of the pattern. But what I interest in the origami folded core is I want to make all the structural component using the composite material. It's a lightweight. So we can tailor, we can change the layup of the composite ply and also change the shape. We may reach it to like a very full capacity of our structure performance. And then kirigami folded core, it's a more kind of imaginary concept. You can see the egg box core and modified corrugated core and then pyramid. So I listed like a origami and kirigami folded core. If you compare the structure performance versus the manufacturability, of course, if you make all the component with a very nice shape, you can achieve to the additional performance increase. However, it's really, really difficult to make it. So there are always trade-off between the structure performance and the manufacturing capacity. So to reach out to mass production, I decided to start with a very simple origami or Miura core origami sandwich panel. And at the Utah State University, I lead the composite research team to make a simple Miura core fold or sandwich panel and to be used that can be used for the UAM structural application. And the advantage over the legacy honeycomb core is we can choose any kinds of folding pattern to maximize or compression performance or the tension performance. And also this folded core sandwich composite has a kind of internal open channel. So if you flow all the air in a cooling medium, we can manage the temperature inside and outside. So there is some potential that the folded core sandwich composite can be used for like hypersonic heat management, all kinds of things. Also, so there is a possibility to redirect all kind of internal, external impact. So we want to maximize the mechanical performance of this Miura folded core sandwich panel by doing a lot of mechanical and thermal testing. This is kind of the a picture of my roadmap. And as I mentioned, I saw the future that the folded core sandwich composite can be used for lightweight, UAM, AAM structural component. So targeting, let's say my first target was, what if we can use this folded core at the wing or the fuselage? And mainly I was targeting to the Supernova from Hyundai Motors Group and the over-air and joint with Hanwha. So at the very first step, we want to optimize the shape of the folded core. What's the proper distance or the height and then the patterns. Once we determine the optimal core design, and then we make the actual part using thermoset pre-preg or thermoplastic pre-preg. And the picture is what we made at my lab. It's an A-ply, carbon epoxy, thermoset skin, as well as Miura folded core application. So we use the traditional composite manufacturing process, but recently we start to make the same structural panel using 3D printing. So not only just using extrusion-based 3D printing, we're also looking at the lamination-based 3D printing, because traditional manufacturing process take at least 1 day just to make small pieces. But if you apply the additive manufacturing for the composite, for polymer, we can directly print the same architecture in an hour. So 1 full day versus 1 hour, that's a huge difference in terms of mass productions. So once we make all the kind of new sandwich panel, and then we did a lot of low velocity impact testing and the hypervelocity impact testing to measure how the structure concept behave at the different environment. So this is an animation that we did hypervelocity impact testing on the A-ply unidirectional carbon epoxy composite, the top two, and the bottom two is carbon epoxy sandwich, fold core sandwich composite. So these composite panels were subjected to the 3 km per second impact, which is very, very fast. And you can see the difference in the debris cloud expansion and then all kind of particle movement. So our intention was to protect all the critical component in the backside. So if you're looking at the animation, the right-hand side is the backside, and the left side will be kind of impact surface. And as I mentioned, the fold core has all kind of open internal core channel. So when the projectile hit the sandwich panel, there are some kind of debris, a secondary impact due to the fracture of the projectile. However, all kinds of debris fracture in the middle section can be redirected inside. That means any component behind this impact side will be safer. That's why we see the kind of very positive result after this super expensive testing. And also, depending on kind of division, you may want to predict what's the kind of the cloud formation of this debris cloud, because that each individual broken pieces can derive the secondary impact. That means the secondary damage. So if you want to predict this kind of all the cloud behavior, we used a smooth particle hydrodynamic code, and each individual particle can be considered as a fragment. So we did some work, and then we have additional modeling and testing going on to evaluate very different performance on this new system. And as I mentioned, the hypervelocity testing is very, very expensive. It can be like maybe $1,000 per shot. So instead of doing all the expensive testing, we want to look at kind of numerical modeling. So numerical modeling must be capture the physical nature of the damage. So we consider all kind of different failure criteria. So the projectile can be metal or any plastic, any kind of material system. But to mimic our testing condition, I use a metal projectile and then model with relevant damage model. And then CFRP, carbon fiber reinforced composites, what we made for the fold core sandwich panel. So we use traditional damage model with the coils below. And then if you're looking at the bottom right side, these two bar graph compare the numerical prediction versus the actual measurement and the impact side and back side. So even though this model is relatively simple, you see all the prediction and test results are quite compatible with each other. What that means, by doing more tuning process, the model prediction can be close to the actual behavior. That means we can save at least $1,000 per shot. And also, when you design the kind of different origami and origami core, I selected 3 representative origami core, starting from standard Miura and indented and curved. And also, I considered 3 different origami core, egg box and the corrugate. So these are all the finite element mesh that we created with my student. And then we run the simulation to predict what's the fiber and the metrics and then all the delamination failure. So simply, if you're looking at the hole, these are fully damaged area. Of course, smaller hole, that means a small damage is relatively recommended when you design your part. So by simply changing the unit periodic patterns of the unit cell, you have a huge variation in the impact, right? So by studying the optimal shape design and also choosing like a different material selection, you may block all the kind of external impact compactly. Yeah. So this one is a matrix damage in the volume-wise. You can see the impact side damage and then through thickness damage as well as the back side. Again, you can see the huge variation in terms of the damage and failure of your fold core sandwich panel. A delamination is simply you have a sandwich panel and then you separate in the applied direction. And then the delaminations are very, very kind of unclear because you can't evaluate the delamination. So this model gives you how much delamination can be driven from the impact. So the red area indicates the fully delaminate, and the blue area means just undamaged and the safe. So depending on the choice of the pattern, you can see less and more delamination after the impact. So if you think about the severity of the damage, of course, the delamination is really bad, and then followed by the matrix and the fiber damage. So concluding remark. So we want to evaluate the dynamic performance of the fold core sandwich panel, and all the testing result and numerical prediction showed these are highly influenced by the core geometry. And both origami and kirigami core can be used, and of course they use a compatible hypervelocity impact resistance. However, if you think about the manufacturability, origami is a way easy to make. Of course, you can make the kirigami very beautiful kirigami core-based structure, but that may be super expensive. So thinking about the mass production of your volume market, and then I think my recommendation for the new structural core will be origami-based. And one of the benefits is the fold core sandwich composite can be designed to add additional functionality by doing core topology optimization. That means you change the shape and the material system, and then appropriate core material selection will maximize structure performance while minimizing the total weight of your aero vehicles. And then I expect our fold core sandwich composite can be used for any kind of commercial aviation industry sector, including jaunt. Thank you.
Thank you to all of the speakers for nice presentation. We needed to arrange the seat for the discussion, so let's have a 5 minutes break. Yeah. All speaker has had the presentation for AAM. The first, do you have any questions for the presentations about the presentation, or any questions about the advanced air mobility? You don't have? You can speak the Korean. I can translate your questions.
I have a question.
Yeah.
To all of the speakers. My name is Yong from Korea Aerospace University. So in order to achieve the eco-friendly and the concept, and then weight reductions for the AAM, the platform. So all of the aerospace industry, and then the steers the demand for the weight reductions, and then some mass production concept is very important. What is the plan, and what is the concept, and for the achieve for any kind of some concept for existing some two world and some AAM, UAM, the platform, the manufacturing systems?
I think the answer is not easy. Who can answer this? Yeah.
Yeah, thank you for the question. I think it's a very important question from a business standpoint to be able to meet the demand in the future, to be able to develop the manufacturing and production capabilities at scale. We see, based on the demand, the need to produce these eVTOLs at a greater rate than aircraft today. And for those reasons, the selection of the material as well as the manufacturing processes are really critical. So we think that a lot of automation, robotic automation, manufacturing automation that already exists today, primarily in the automotive industry, will be essentially critical for the development of these aircraft so that we can mass produce these aircraft. Obviously, the low rate initial production will start at a certain level and then increase over time. But we envision thousands of aircraft being produced per year, and the driving factor in terms of the assembly time of an aircraft is typically the fuselage, the airframe itself. before you have to stuff it with all sorts of systems. But the long pole in the tent, so to speak, is the fuselage. And so the ability to, in our case, we're using thermoplastics. We're able to hot press form panels and then use induction welding. And all of this is done through robotic automation. Want to minimize the touch labor, same as, again, the automotive industry. The fewer humans are involved, the faster things go. So I think that's one of the driving aspects for mass production.
Can I add a little more?
Yeah.
Yeah, that's a really good question, because right now all the people are crazy for the UAM and the kind of AAM, but the production capacity nowadays is very, very slow. That means maybe in the current plan, I mean, at the current status, we can build maybe one UAV or the UAM system per maybe a week or a month. So it's really, really kind of like difficult to create that kind of revenue from the market. But if you think about the near future, that means the next 3 and 5 years, of course, we can use kind of legacy aerospace composite material system that are already being certified. So you can simply change this material system in next 3 and 4 years. The problem comes with the certificate. If your vehicle is not certified, you can sell it to the customer. But if you think about the long-term plan, like after 5 years and 10 years and 20 years, when we develop all kind of fast, advanced manufacturing process, we can make maybe UAM airframe maybe in maybe in 1 hour, 2 hours, using thermoplastic resin system and combining with additive manufacturing and the snap cure resin system. So right now, very, very little kind of small size market, but we have a very bright future expectation, and both in academia and the industry. So the future, there is a very infinity amount of the potential. But right now, we need to go do every single we need to check every single items to make all the vehicle to be certified. Yeah.
Do you have other questions?
Yeah, can I comment? So
Yeah.
it seemed like there were 2 parts to your question. They know a lot more about the manufacturing, but I want to comment on the sustainable operation a little bit. One of the reasons that I think it's really important to go after the autonomous contingency management as opposed to having continued use of a pilot on board the aircraft is you are using a tremendous fraction of your usable payload for that person to sit on board, and they don't even need to go to this next destination. They're there to fly the plane. So you immediately get a savings of maybe 1 in 4, 1 in 5 passengers by moving that person to the ground. And it's only through certified autonomy for contingency management that you're going to do that, because that's the missing thing now. The other thing I want to say, and this is the second part in airspace, flying direct is always more efficient than flying in corridors that have been predefined that may not even be close to direct. So we have to figure that out. How do we actually prevent the small UAS from needing to go between buildings, scaring people and going very non-direct trajectories? Well, the only way to do that is to move them up. Passengers don't want to go skirting between buildings. They will feel unsafe, whether they are or not. So we have to figure out this airspace integration problem as well, and we have to do it in a way so that these vehicles can fly their optimal routes. They're going to have different speeds. They're going to have different profiles for climbing, transitioning, descending, and they're going to have to share the airspace. So those are all challenging problems independent of sustainability. But if we throw sustainability out as a consideration, we're going to end up with solutions that really are very suboptimal in terms of energy use.
Thank you. Do you have any questions? Other questions? Yeah.
Yeah, Deongli, Nano System. First of all, thank you very much for your nice presentation for speakers. Actually, I'm wondering about the current UAM or the AAF. Yeah, whatever. What about the current thermal management system in the UAM or the AAF? Or the technology trend or current address for the thermal management systems?
I think that there is no people to heat management or the thermal management for battery or other systems.
That's another critical area. So in terms of the differences that we see with eVTOLs, all electric, there's hybrid as well, but the all electric aircraft, the big difference is they have batteries. Batteries that are very heavy, very with high, energy density ratios. And one of the great concerns is thermal runaway. And so cooling and the ability to minimize the propagation of any incident between cells is a leading factor in terms of certification and of course safety. And so there's ongoing testing right now with all of the key battery manufacturers. We see in electric cars, that this has been addressed. However, when you're thinking of aircraft, the amount of energy is 10, 20 times. These batteries are enormous, and so that's a major factor. And of course, when you're flying, you can't just, if you have an issue, you can't park your car or your aircraft. So mitigation is a major concern.
A few people ask some questions online. So one question is, what do you think is the biggest obstacle to the development of AAM technology? Who can answer this question?
I think in terms of the manufacturing the UAM or AAM product, right now, I mean, we have a very bright future, but if you think about the current market size, we have no market. So that's all the academia industry actually try to spend a lot of time and the money to build our kind of market size. So the best obstacle will be, it's kind of the UAM is a conjunction between the automobile and the airplane, and that means we need all the experts from the two different disciplines. So it's not easy task, and also there's no visible target market, and also no plans. I mean, yeah, Supernaut is targeting release something in 2028, but except for that, yeah, all the people are crazy for the UAM, but right now, nothing to show you guys. That's one of the big obstacles to me. What I'm thinking.
Yeah, I think you need to ask that question two ways. One for package delivery, and the other for people delivery. So I think the answer is going to be different in both cases. I think package delivery is going to be very soon. It's already been tested, and maybe you would like to comment on that. People delivery, I think, is going to be a stepwise solution that I think Ella has a great question. You should ask it, not me, but basically how many of you would get in even a car today that has no person inside and is completely autonomous? Would you raise your hand if you would do that? If it were the first one? Okay, so the answer is no. So I think that stepping through the people moving market is going to be much slower than the package market.
Can I just make a brief comment? There is actually an urban air mobility market today, and it's helicopters moving people. The problem, it's expensive, it's noisy, and it's really not accessible for most people. So the initial, I wouldn't call it obstacle, I would say challenge for electric vertical takeoff and landing, electric helicopters effectively is introducing the new part of it, which is charging, right? So electric charging infrastructure is going to be a challenge, but there are technology development solutions in place for that. But that's one of the areas that we see infrastructure initially retrofitting aviation infrastructure with charging for these types of aircraft.
So in terms of a logistic perspective, this is just my personal thought. So if you look at the AAM and logistics, right? We need to use the AAM in the many different ways. It means that last mile deliveries or middle miles. If you think about middle mile portions, basically moving the volumes between hub to hub, right? In this case, we need to thinking about how we can land the eVTOLs and then how we can move the volumes from the landing site to the inside of a warehouse, right? That's very critical. If you see UAM domains, many people think, talking about like body port, right? How about logistic body port? How we can have a seamless integrations. Another aspect is power perspective. So microgrid is very critical, and also if you see like logistic operations because of weather conditions, sometimes we have power outage issues. This is very critical, and I truly believe that we need to think about how we can minimize those kind of technology and operational gaps.
The second question is for Dr. Che. What do you think is the possibility of drone and UAS, UAV for the logistics? This question is online.
So again, this is my just a purely personal answers. We have a flight for the team. They are working on like those kind of details. But personally, I just mentioned that there's a market. We can use small drones for residential deliveries or express deliveries, like medical equipment, right? But the challenging part is regulations and public acceptance. Because if you talk with the actual people, residential people, they don't want to have a drones flying on top of their house, right? That's a like existing challenge, right? But I think a more realistic use case can be minimized. I just mentioned moving the volumes to hub to hub. That's more real term we can think about. Also, there is a sustainability impact. It means that traditionally we use the airport, right? It means that we need to move the volumes from the hub to airport, right? Using the trailers, and then using the aircraft, right? And then we need to use another trailers, move the volumes from the airport to hub, right? Now, if you can use the eVTOLs, we need to cut 2 trailers, right? Then we can save the money, right? Second aspect is we can have a more better like sustainable solutions because we don't need to operate the trailers.
Thank you. Is there any questions? The Korean government ask us, company, engineer, professor, that commercial, the UAM operation start next year to 2025, commercial the operations. So I would like to ask to the Professor Chrudos, how do you think about that? When and how is possible the commercial operation of UAM in UK?
Well, for cargo, we already start using that one because Royal Mail it's already operate with deliveries already. Now, urban air mobility for people it's slightly. We don't having the target for next year in the UK. We're having demonstrations for next year, but it will take a little time to integrate not the platforms but also the vertiports into the country, which we don't have in UK. We don't have heliports ready, so we need to build them as well. So a little longer for us.
I agree with you, but my government doesn't agree. Do you have any questions about the presentation or any questions about the AM, UAM, drone, anything?
I have a question about active avoidance, collision avoidance kind of, or contingency control, as Ella said. What about active movement of the vehicle to avoid some contingency situation. Like I guess morphing, shrinking wing is one of the example, or very agile attitude control can be another example. What's your you guys' opinion about that?
So when an aircraft has an emergency, it has priority. If it calculates a safe landing solution and there's an emergency, then that's a special situation. If you have data link and are able to immediately share that solution, every other aircraft, every air traffic control station in that area knows the plan of the emergency aircraft. I didn't talk about this, but the next step then is for anyone who's on the ground at that landing site, let's say it's a runway, any aircraft that was cleared to take off will leave the runway, and any aircraft that was planning to land on that runway within the time of the emergency will divert and go away. That, as long as you don't have many aircraft with emergencies in the same place at the same time, that works. It's unlikely. We hope that everything is going to be safe, right? When we certify all these vehicles, we're not going to have an airspace that's crowded with many emergency aircraft. So that should be okay. Now, I think that what you said, the adaptive control, the envelope estimation, all of this operating together coherently, that's the type of thing that we need right now to have a human and software working together for. We're going to be getting more and more sensors over time, which is going to give us better diagnostics, prognostics, not only for maintenance, but also so that the health of the aircraft is known by the flight control system. With that, we're going to have more advanced warning as to things that might go wrong, like low battery energy, overheating batteries, and a myriad of other things. The idea then being that if you have an estimate of how long you have before something goes wrong, you don't ever have to declare an emergency. You instead would declare an alternate flight plan, and you would have time to get that coordinated with everyone else. So the emergency, again, should be really rare, and the reason it should be really rare, even with a high-density airspace, is because you have advanced technologies. The advanced is not only in the airframe and the electricity used to power it, but also in the software and the sensors that are making it more capable, more aware, able to make better decisions, able to communicate them immediately. So that type of technology working together can make it safer. In terms of collision avoidance, I didn't talk about this here in the 10 minutes, but I did when I gave the talk earlier. You have to have data link. And the data link can't just be ADS-B. It has to be what is done by voice today, right? And with that, the delays tend to be milliseconds instead of many seconds where you're speaking and at the other end of the radio, the human has to interpret what was said, right? That is a very slow process. It doesn't have to be that way. So that is really a key. If every aircraft was sharing data on its intentions as well as any problems that it has, the priorities can be immediately set, and the collision avoidance can occur not by a desperate maneuver, but by making sure that the plans are coordinated.
I think only thing that we need to remember that we're having people there that they will not be pilots if it's autonomous, and sudden maneuvers, it will scare them. So we need to be taking into account that we need to have the comfort of the people on board, and the trust that they will not see something that they don't expect, because they will react as well.
Absolutely, and I think the data link helps you do that because you're able to react before things get bad.
Well, I couldn't agree more about the need of the contingency management plan, especially for the autonomous operation of the AAM, because everybody wants to remove the pilot cost. But my question is, in order to be really useful, then you need to have a real-time data of the capabilities of the current aircraft, including the battery reserve whatever the malfunction of the components, and also you need to know the climate condition, including wind speed, and also on the ground condition, the density of the population is changing, especially in the urban area, depending on what time, right? In nighttime, the central part of the downtown is probably very empty. So, I mean, you need to have a lot of data links. Also, you need to have a lot of sensors on the aircraft because you need to be in good command of the health monitoring. So my final question is, which will be more economical? That will require a lot of investment or the cost of the manufacturing in order to enhance the safety of the aircraft, whether that will be cheaper than the pilot. So, I mean, obviously, eventually we'll be there, but what time will be there? That's my question.
Well, so the timing has several aspects to it. One, which was mentioned earlier, is when are people ready to not be afraid of flying in an aircraft that doesn't have a human pilot on board? And that may be a longer time frame than it takes to actually feed back all of the sensor data that's used for health monitoring and maintenance today in a way that helps the autopilot make wise decisions about contingency management. But I think no matter who is flying the aircraft, autonomy, pilot, both in cooperation, a lot of what you said still needs to be done. Whether you're looking at cell phone data about where the people are and are they sheltered versus not sheltered to give yourself real-time population information, that's going to be really super useful for every advanced air mobility platform, whether it's controlled by a pilot or automation. And furthermore, maps, better maps than we have now, that have details and really super accurate models of cell tower locations, power lines, all of the really dangerous things that sometimes rotorcraft and aircraft hit today. You need all of that, and it doesn't matter whether it's a human pilot or autonomy. The human can't see them, and we're also challenged to get to anywhere close to 100% and seeing them with perception systems because they're thin and narrow, and the point clouds don't have a lot of density in reflecting off of them. So these are challenges that continue to be for everything, and they're going to slow it down. But the data and the time to process it favors the software, because the amount of time that it takes software to read an existing map database that goes beyond the line of sight of your sensors on your aircraft, but that also incorporates the sensors on your aircraft to give you situational awareness of your environment immediately while you're there, as you're on approach, for example, to your landing. That information is rapidly becoming what I'll call superhuman. And I don't mean like superhuman like it can fly like Superman, right? But I mean that the sensor data is pervasive everywhere, and the decision making is done faster. And that's happening right now. All of the AI that, for example, is done at UPS is doing a lot of this work, not only for the aircraft, but ground and packages and that sort of thing. So that's part of it as well.
Thank you.
And I think for the ground that you say, the information, this is already done because, the cities like the one we're working in UK, they start looking that they need to do that anyway for the ground vehicles. Autonomous, they need to know where it is, everything there, where is the traffic, where it is the people, how to, so it is how to connect this data in the traffic control for not only for the ground vehicles, but for the cities, from the airspace, for the platforms, and it's happening already. So I think the different parts, it is there. How to connect the different dots, that's what I think Ella is saying. And AI is moving. You're doing more than we do already.
Yeah, one thing I want to highlight that Ellen and we discussed, who is leading the creating the map data? That's a very important topic, right? Because we want to have unified, very uniform map data, right? But if government start to control, then we cannot grow our industries, right? Then how we can balance, right? Government to chime in, hey, this is a kind of standard, right? Then new startup and industries can build their own map data to provide very unified the map information so that we can build a very safe AAM infrastructure.
Thank you. Time is done. Do you have any questions? Last question? If not, I would like to close this BrainLink X Lab Day talk concert. Yeah, thank you for coming here and joining this BrainLink X Lab Day talk concert. Thank you again.